Max and min. So thinking of just a regular max and min, when you have a graph and you have a maximum or a minimum somewhere, what characteristic we learned about in calculus happens at a max or a min? Slope is the tangent. The slope at a max or a min is 0. Is 0. Okay, so that's going to be a big concept we're going to use for a max or min problem, is where the slope is 0, where the rate of change is 0. It's a little bit different than a rate of change. So these are called optimization problems. So things like, what is the maximum profit for a possible business? You would use this type of concept. Minimum cost for building a pipeline, maximum volume of water, a container with a certain amount of material. So for obvious reasons, we also call these max and min problems. All right, so there's some stuff you need to write in. Sorry, I didn't give you a purple sheet. So the first thing is we want to identify what we're trying to maximize. So identify the max min variable. So let's call this variable q. Yes, why q? I don't know. Why not? Okay. X and Y need a break sometime. Okay. They need a holiday. Then after that, this is a very powerful step, which you should be doing anyways. Identify all other variables. Place them on a diagram, if possible. So because if q is the variable I'm trying to maximize, I want to make an equation with q in it. So find an equation describing the max min variable. Is 0.3. Find an equation describing that max min variable. Okay, if q is described in terms of more than one variable, this is very important. So if q is described in terms of more than one variable, for example, both x and y. So q is equal to q squared equals x squared plus y squared, say. Say we are trying to maximize a hypotenuse. That's a problem if it's described in more than one variable. Okay, we always want to make it in terms of one variable. So how do we do that? How do we get rid of one of those variables? We need to find a relationship between those other variables. So find an equation between the variables x and y in this case. Isolate one of those variables. Isolate one of the variables. So there's got to be some relationship between, they'll have to give you some information between x and y. So if we were doing like q squared equals x squared plus y squared, they also told us that x is 2 times y. Okay, twice the size of y. So there's some sort of relationship between those two variables so that our equation should only ever have two variables in the end. The variable we're trying to maximize and one other variable. That's our goal. Okay, an equation with two variables. The one we're maximizing and then one other one. So substitute this back into the original equation. If you are successful. If you did your work properly and if you are successful. Sounds like a mission. If you are successful, you will be be a function of only one variable. Okay? So what does this do? Well, if Q is only a function of one variable, we can basically have a relationship between Q and that one variable. Whatever Q is, whatever we're trying to maximize. And so then we can do this really cool thing. We can actually differentiate with respect to that one variable and find our maximum for Q. Okay, so use the first derivative test. What was that? I need to add some humor to this video, I feel. Yes, we are recording. We are live. To find the max min value. So how do we do that? Find the derivative of Q. Sorry, it's a lot of writing. I should have just photocopied it. You may have to implicitly derive okay. Find the critical values. So that's when our derivative is equal to 0 or undefined. But we want specifically 0, right, for a max min. And then find absolute max or min. And state your answer in words is the last step. Again, yes. Therefore, it's a lot of writing here. Okay, so essentially, figure out what we're trying to maximize. Make an equation with that. Somehow make sure that the equation only has one variable other than the variable you're maximizing. Differentiate. Set your derivative to 0. Solve. Write your answer. That's it. That's all you gotta do. That's it. That's it. Okay. I think people like max mins a lot better. Yes. Some people out there. Okay. So let's look at the next question. So we're not differentiating with respect to time anymore because it's not a rate of change. We're just trying to maximize some particular variable. Okay, so find two numbers whose sum is 34 and whose product is a maximum. So what are we trying to maximize? First step. What are we trying to maximize? A product. So we need a formula for product. And what are we multiplying? Two numbers. So give me a formula for product. Product equals x times y. Okay, because that's what I want to maximize. Now, right now, do I have only two variables in an equation? What I want to maximize and one other? No. Uh-oh. Is there some other relationship between x and y? X plus y equals 34. So which variable would you like to eliminate? Y, sure. Why? Because I said so. No, just because Amy said so. Whoever did. Did I do something wrong? Whose sum is 34? Yeah, so 34 minus x. Okay, so what are we going to do with that y now? Place it back into our original equation because we want to eliminate one of the variables. So y is equivalent to 34 minus x. I mean, you could probably think, this is just a very basic going through the steps. You could probably solve this one without using calculus, okay? Okay, so can we simplify that equation before we differentiate, or do you want to use product law? Simplify? Okay, I thought so. 34x minus x squared. Okay, so we want to differentiate. We're going to differentiate with respect, so we're relating Right now I'm going to relate product with one of the numbers, x. So we're going to differentiate with respect to x. Why is this a wonderful differentiate with respect to x? When I derive x, do I have to multiply by dx dx? No. It's 1, right? Change of x with respect to x is just 1. So we don't have to multiply. We don't have to include that. So handy. Okay, so that equals what? 34 minus 2x. And we want when our product is a maximum. So right now we have a relationship between product and x. And there's some relationship. It is quadratic. And we want when the product is maximum. So that's when our slope is 0. So we set our derivative to 0, and then we solve. So add 2x to the other side, divide by 2, and x is 17. So what's the other number? And y would have to be 34 minus 17, or 17 in our last step. Therefore, the two numbers are 17 and 17. Yes, Q is our P, because that's what we're trying to maximize. Okay? Yeah, it's very similar to your max, well, except for before you didn't use different, you actually did completing the square, right? Because they were quadratics, and then you found your max, probably, yeah. You probably dealt with this type of problem before too. A farmer wants to enclose the largest possible rectangle pen for his chickens using 300 meters of fencing. Find the dimensions of the rectangle if he plans to use the barn as one of the sides. So we have the barn. It's a rectangle. So let's draw. Well, first of all, what are we trying to maximize? Area. So we need a formula. Because we're trying to maximize area, I'm going to need a formula for area. And what shape are we dealing with? A rectangle. So what is the formula for area of a rectangle? Length times width. So let's draw our picture. So we have can we differentiate right now? No, we want to only have an equation with two variables. So is there a relationship between length and width up there somewhere in our word problem? Perimeter, 300 meters of fencing. So now, is it one length or just two lengths? One length plus two widths equals 300. So which variable would you like to replace, your length or your width? Now, if we do length, it's already L, like coefficient of 1. So let's replace length to be 300 minus 2w. I can move this up, sorry. So our area equals, our length is 300 minus 2w times our width of w. And before we differentiate, simplify it. So now our equation is relating area with width. We're comparing area to width. So we're going to differentiate with respect to which variable? Who's like our x this time? The w. So the change of area with respect to the width is equal to 300 minus 2w. Oh, did I do something? Oh, yeah. Okay. That's better. Okay. And now what? Because we're maximizing area, what's the rate of change of area with respect to width? What's the slope of that? This is going to go to 0, right? if we're dealing with relating area and width, and that's the equation, we want when that rate of change is 0. And that's easy, right? So I find it's a lot easier to use derivatives than it is to do the same problem and then having to complete the square. Back in grade 11, that's what you did. Okay, so add, right? Isn't that what you did? Yeah, and then found your vertex? Or use your calculator. Let's be honest. So 75 is your width? 75 meters? Okay, what's your length then? Length equals 300 minus 2 times 75, so it'd be 150. So therefore, width of 75 meters and length of 150 meters would maximize our area. Okay. Okay. Next guy. I need you to change. Did I change this yet for you? Let's see here. Does yours say 100 kilometers per hour? Can we change this? But 100 is easy too. Okay, we're going to change this to 100. This to 300. And this to 90. That's more realistic. A train leaves, or just make it joggers. I guess so, hey? A train leaves Edmonton at 7 a.m. and travels directly east at 100 kilometers an hour. At the same time, a bus that is 300 kilometers directly south of Edmonton travels towards Edmonton, north, at a rate of 90 kilometers per hour. At what time, to the nearest minute, will they be closest together? Whew. Okay, so the question is, are we trying to minimize or maximize something? We're trying to minimize our distance. Specifically, well, we need to draw a picture. So let's draw a picture here so we figure out, okay, what distance. So we need a relationship with distance. Okay, so we have at the very beginning, you're welcome. We have a rate of change, sorry. Yeah, we're good. He's traveling at 100 kilometers per hour. And at the same time, there is a bus. He is traveling 90 towards Edmonton. And how far apart is, oh, there's 30 kilometers between them. 300 kilometers is the distance. It's, 300. Okay, so this distance here is 300 kilometers. Okay, and so at some point, we want when their distance between them is minimized. Okay, so that distance, what do you want to call that distance? D? Okay. Okay, so this, in order to find a relationship, this has to be some distance here, right? So that we have to find a relationship between all of this. But we need a formula for D. Okay? And we need the same variable. So right now, if I go x squared and y squared, will that work? D squared equals x squared plus y squared. So for minimizing distance, D squared equals x squared plus y squared. Does that work right now? Is there a relationship that we know of between x and y, really? Well, they're moving at different rates. We want to know what time that happens. So that's a hint. It's not going to be the same. Because they're moving at different rates. Is there a way to relate them in terms of time? Use time as our variable. So this variable would be 300, your distance. So this distance right here would be 300 minus and 90 times 90t, rate times time. Okay, that would give you this distance here. This distance here, what would that be? 100t, your rate times your time. So now do we have a relationship? Yep. So remember, distance equals rate times time. That's what we're using. D squared equals, so x squared, I don't know which one's x. Doesn't matter. 100t, sure. Horizontal. 100 squared plus y is 300 minus 90t squared. Now, we could simplify this if you wanted to, but we can go straight to differentiating. Now that we have, this is what I'm maximizing or minimizing. I want to minimize a distance, and I have only one variable. I have two variables total. So can we go straight to deriving? Yes, because this is going to be ugly to simplify. So let's just derive this. Derivative of d squared. 2d times dd over dt, and that's what we're trying to minimize. Equals 2, keep the inside the same, so it's power law, power of 1, times the derivative of the inside is 100, and we don't have to write dt, that's equals 1, because we're differentiating with respect to time. So we can keep going, plus 2, keep the inside the same, power of 1 times the derivative of the inside is negative 90. Okay, a few things we can do to simplify this. Tell me one of them. Get rid of the 2 and divide each term by 2. Yeah? What else? What are we setting to 0? dd over dt, we're setting to 0. So d times 0 is just going to give you 0. 0 equals 100. T times 100. Why not just simple? 10,000 t plus, bring in the negative 90, I guess, hey? Is that okay? Am I doing too much? Are we good here? Okay, good. Negative 90 times 300 is negative 27 and 3 zeros, 27,000. Negative 90 times negative 90 to the power, negative 90t plus 8,100t. So this is easy to solve now. Just pick numbers. We're not afraid of those. Move 27,000 to the other side. 10,000 minus or plus 8,100. What unit will our time be in? Hours. Are they asking for a specific time? To the nearest minute. What's wrong? That's right. Well, I think it's right. I think it gives us 1.49. Let's divide them. So to the nearest minute, $1.49 hours Or if we want the time, subtract the 1, because it's 1 hour, and then to convert the decimal of an hour to minutes, times it by 60. So it'd be 1 hour, and it actually rounds to 30 minutes. Okay, so they are closest together at what time? At 8:30 a.m. because they left at 7. More for today, and that's it for today. Unless you wanted to keep going. Let's not say we did. Okay. Find the closest point on the function y equals 3x plus 2 from the point 2 and negative 2. So let's just draw this really roughly. Okay, so the point, we have an equation 3x plus 2, so the y-intercept is 2 and a slope of 3. And 2 and negative 2, there's some point P. What are we trying, if we want the closest closest point, find the closest point on that function, are we trying to maximize or minimize something? Minimize what? Distance. Is there a formula for distance, a point, distance from 2 points to a line? Remember, did we learn about one this year? Distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. It's really Pythagoras, right? So we have a formula for distance. Is there anything that's staying the same in this formula? Okay, we know for sure the point is always 2 and negative 2. Could we sub that in? Yeah, sure, let's do that. Start. X minus 2 squared plus y, take away negative 2 becomes plus 2 squared. Are we ready to differentiate this? Because we want to minimize distance. No, why? There's 2 variables inside. Well, there's 3 actually. We only want total 2. So how do we replace one of the variables? Y is equal, this is so easy. Y equals 3x plus 2. So we can replace y. Do you want to make it a lot prettier? Get rid of the square root? Let's do that. But I'm going to insert first y. 3x plus 2 plus 2. Or 3x plus 4. So I'm going to square both sides to get rid of that square root because it'll make differentiating a lot prettier. Okay, so now do we have an equation with 2 variables? Yes, including one we want to actually minimize. This is another way to solve this problem. Okay, there's other ways. We've learned other ways. This is just another way. So differentiating this guy, d squared would become 2d, and then what are we deriving with respect to? Which variable? X. So we would multiply by dd dx equals, yes. You could like FOIL it all out, collect like terms. Might be easier. Yeah. Because you have to use chain rule here, right? 2, leave the inside, power of 1, and then times the derivative of the inside, which is just 1, plus, again, chain rule, so power 2, leave the inside, then power of 1 times the derivative of the inside is 3. You could still do some simplifying. What could we do? You could take the what? All the 2's, divide all terms by 2, and then dd dx is actually going to be set to 0. D times 0 is 0. So I have 0 equals x minus 2 plus 9x plus 12. If you bring in the 3, and don't forget that 3 there, derivative of the inside. Or 10x plus 10. So x is negative 1. So we found, how do we get y now that I know it's x is negative 1? Plug it, sub it in. Y equals 3 times negative 1 plus 2, or 1, negative 1, sorry. So what would be the nearest point? Nearest point is negative 1, negative 1. Yep. This is not the only way to solve this problem, but it's one of the ways. Okay, guys, how did you find the max min stuff? Easier? Well, okay, so you'll notice that the homework accidentally got pushed to the next page. Again, I'm sorry. So it's there. We have 20 minutes left. Start working on that. And then tomorrow we'll do 3 more max min questions that are a little bit more interesting.